Okay, let's begin our story of circle-ometry back at the dawn of time. Imagine humankind back, plonked down in this universe, sitting on the ground and thinking to himself or herself, what is this universe I'm in? What's going on? You know, they might notice things like at night the sky is littered with little pinpricks of light called stars. They might notice they actually are shifting across the heavens. They'll notice the moon is moving across the heavens. During the day they'll see the sun that always seems to rise in the east, go in some great big arc overhead, settle down in the west 12 hours later, and presumably 12 hours later again repeats that cycle as a great big arc of some kind. So it became a very natural question for humankind. What is it about these heavenly bodies I see? So I'll focus on the sun today, but they could also ask about the stars, the moon, all sorts of things. What can I understand about the heavenly bodies I see around me in this universe? And a very natural question about the sun, for example, would be, well, physics questions like, what is it? What is that thing up in the heavens? Why is it hot? How does it stay there? How does it move? More mathematical questions of interest to us is like, how far away is the sun? Or maybe another question is like, how high is the sun? Could I actually go up to the sun and figure out its height? Well, no, I can't. I mean, I can't go up to the sun, drop down a rope and figure out its height. But you can imagine a question like that is a very natural question. How high is the sun? So in some sense, that's the beginning of our circle-ometry theory. How can I possibly figure out the height of a heavenly body as it moves across the sky? Whoa, okay, so what can I do here? Well, first of all, I think to note that I can't actually measure the height. I might want the height, but I can't measure it. The only thing I can possibly measure from being down here on Earth is not the height of the sun, but maybe the angle of elevation at which I spot the sun. So maybe I can say, all right, right now I'm seeing the sun at an angle of elevation of 40 degrees. That's the only thing I can actually measure. And I'm wondering, from that one measurement there of angle, could I ever work out the height of the sun at that particular height when it's at that angle of elevation? And that became the basis of a theory of circle-ometry. Now, scholars were fully aware that the sun does not move a perfect circular arc over the day skies. But just to get the theory going, they said, look, we'll get it going. We'll assume that the sun follows a perfectly circular arc, get some mathematics going for that, and then we can adjust that model for what's really going with the sun when it might be a slightly off circular path. That seems fair enough. Great. So we did that. Oh, by the way, that actually motivates mathematics. In fact, so much of mathematics is motivated by astronomy for this very reason. Have you ever noticed in your classes that when we draw the four quadrants defined by two axes, the x-axis and the y-axis, we actually number the quadrants 1, 2, 3, and 4. And if I said to you, please number the quadrants 1, 2, 3, and 4, the very natural thing to do would be 1, 2, 3, 4. In fact, we don't. In mathematics, we don't do that. Well, first of all, we use Roman numerals, but we actually label them this way, in this funny way: quadrant 1, quadrant 2, quadrant 3, quadrant 4, which seems very unnatural, very weird. But that actually is very natural for us because it comes back from trying to understand the motion of heavenly bodies. If I look at this, we've settled upon the convention to always put east to the right in our maps, and from that, look at the motion of the sun. The sun always rises in the east, and it first moves through that quadrant, then it moves through this quadrant, second quadrant, then it moves through this quadrant, third quadrant, fourth quadrant. So in mathematics, to mimic this, it became very natural to think of, that's the first motion of the sun, second motion of the sun, third motion of the sun, fourth motion of the sun. Let's actually number the quadrants based on the motion of the sun. That's where that comes from. A very human reason. Also, you notice that mathematics tends to go counterclockwise, which is really weird because the rest of the world with clocks goes clockwise. Why is maths doing the opposite? Well, think about it. It's actually a good human reason for that too. What's one of the earliest types of clocks that we humans ever invented? Well, it's basically a stick in the ground and measuring the shadow, a sundial. And actually, if you do stick a stick in the ground, here's a stick, it'll cast a shadow. It's worth doing this one day. Actually go outside, stick a stick in the ground and watch the shadow. See what it is 1 hour, come out an hour later, see what it's another hour, and you'll see the shadow actually moves this way. So actually, for notions of time, by following the motion of shadows, it became very natural for us to associate this direction with time, even though mathematics was going in this direction because of the mathematics we were setting up here. It all makes perfect sense. In fact, if you get a upper level of maths, you'll find that we always measure angles from the east, from the direction of the east. Angles always go this way. It's considered a positive angle, whereas going this way would be considered a negative angle. We always measure angles from there because we're just mimicking the motion of the sun. Mathematics is back to the human question here. Whoa! By the way, I have to point out, I'm Australian. If you stick a stick in the ground in Australia and watch the shadow move, it actually goes the other direction. So actually, if Australians ruled the day, time and mathematics would both go the same direction, everything would be in sync. Just saying, just saying. All right, okay, but back to our story, So you may want to say, how could I possibly figure out some basic information like the height of a sun when there's only one thing I can possibly measure is the angle of elevation at which I sit here and look at it? Hard. All right, so just to get the theory going, people actually got some stuff happening here, but they had to make one assumption. They don't know what the radius of the circle is. So just to get the maths going, let's just choose a very simple radius. If I ask you to choose a simple number for radius, it's very natural to choose the number 1. Because no one likes hard work, always go for the easy numbers. These are mathematicians, never do hard work. Make it easy for yourself. So let's just call the distance from me on Earth to the Sun one great big astronomically big unit. And by the way, astronomers do call the distance from us to the Sun 1 AU, 1 astronomical unit. So actually that is 1 AU. Whoa. Okay, all right, so that's it. So that's the name of the game. Could we possibly work out the height of the Sun, assuming we're in a big circle of radius 1, when all we know is the angle? Now, this is a very hard challenge. But actually, the history of maths here is really quite deep, because around the 5th century, around the 400s and so forth, this became a really big topic in India. They actually figured out how to work out the heights of the Sun at different angles of elevation. And it was great. And they actually wrote great big texts and volumes of books, all in Sanskrit, actually describing how to work out the height of the Sun for certain different angles. Know they actually gave this height a name. They called it the Jya. Actually, I think it's Adha as well. Now, forgive me, I don't actually know how to pronounce Sanskrit, and I'm also trying to write Sanskrit in English, so I'm way off here. But they called it a great big long name, which actually meant, well, okay, the history is a little bit confusing here. This is related to the word bow. Like, they can imagine, like, you kept this picture going, you can actually see that this picture is part of a bow and arrow, but then it also became later known as just the half chord. So this height became known as the half chord. And you can kind of see why it's called the half chord, because that height, oh, I just erased it, is half the chord of a circle. So they were trying to work out, okay, I bet we can work out the half chords at different angles, and they could. They got some angles going here. Now, of course, it gets tiresome to write great big long words. They actually abbreviated it to just Jya. And so they'd say the Jya of 40 degrees is the height of the Sun at an angle of elevation of 40 degrees. And then maybe you do the Jya at 30 degrees, the height of the Sun at 30 degrees. The Jya of 80 degrees, the height of the Sun at 80 degrees. The Jya of 100 degrees would be over here, 100 degrees the Sun would be out there, with the height of the Sun at 100 degrees. Bingo. Mathematics was fabulous, really taking off in India around the 5th century there, and kept going. Amazing mathematics worked out there. But then, mathematics really started taking off in the 800s, 900s in Persia, Middle East. And those Persian scholars saw all these incredible texts in Sanskrit in India and said, these are amazing. Let's translate them into Arabic, our language, and we'll carry on with the maths. And they did. So they took all these volumes they saw in Sanskrit and translated them to Arabic. And they saw this shorthand for half chord, for this height of the Sun. They said, okay, that's just shorthand, that's not the full word. But they said, okay, we'll just copy that shorthand letter for letter from Sanskrit into Arabic. And they did that, and they got something like Jiba. And of course, now I'm trying to write Arabic from Sanskrit in English. I'm in trouble. So anyhow, it's something like Jiba. So there's in 800s, 900s, and so forth in the Middle East. They kept going. They translated all this text from Sanskrit into Arabic and kept going with the maths and worked out the Jibas of more angles. Got this theory really going. Absolutely fabulous. Now, here's the thing. Of course, they wrote their books as well, but ink and paper was very precious. And it was a very a standard habit amongst Islamic scholars to actually save ink by doing this. Don't bother writing vowels. They just went JB. Because actually, try this. Write a passage of text in English without any vowels. And I bet you can still read it pretty well. So if ink is precious, you can actually get away with not writing the vowels and still figure out what the words are saying. Interesting. So they just went JB. So they abbreviated JB. And they had a grand time working at the JB, the heights of the Sun at other angles of elevation, 1 degree or 15 degrees or who knows what they were doing. But they really advanced this theory of circle-ometry even more. Fabulous. And then around the 1200s, mathematics really started taking off in Europe. And all the Western scholars there went down to Madrid, which was Islamic at the time, and saw these incredible texts in Arabic, figuring out the height of the Sun at different angles of elevation. And he said, this is fantastic stuff. We need to translate those texts into our language. Now, the scientific language at the time in Europe was Latin. But then something curious happened. They saw this JB and thought, JB? They knew that the vowels were missing, but they said, well, what word in Arabic is this JB with some extra vowels? And they could only think of one word, something like Jayib. Maybe with a Y there, could be with an I, I'm not quite sure. Jayib. And they said, well, they didn't recognize this was shorthand for another word. They said, Jayib. That's weird, because a Jayib means a little twisty bit. A twisty bit. Like, it's often used in different sentences, different contexts. For example, a fold in a piece of clothing could make a little pocket. So that little twisty bit of clothing could be called the jayib. Or like in a coastline, you've got a little twisty coastline, you might have a nice little twisty place to safely put your boat at night. So it could also mean like a cove, a little place of harbour. So a twisty bit, and they thought, hang on, why are they calling the height of the sun at an angle of elevation the twisty bit of the sun at that angle of elevation? Weird. Nonetheless, they said, okay, we don't know why they call it the twisty bit. We'll just use the Latin word for twisty bit. Strange. The Latin word for twisty bit is sinus. And they would say, let's call the height of the sun at 40 degrees the sinus of 40 degrees, the twisty bit of 40 degrees, which is really weird. Actually, by the way, we know the word sinus in English as the twisty canals behind our nose, the sinuses, exactly that word. And then eventually, from Latin to English, sinus became sine of 40 degrees, which we abbreviate that, just a three-letter notation, to sine of 40 degrees. We call the height of the sun sine of that angle. Whoa, whoa. So for a beautiful piece of mistranslation in this human story of mathematics, the height of the sun is called the sine of the angle, and that literally means the twisty bit of the angle, which makes no sense. Whoa. So welcome to the story of circle-ometry. So in the end, so all it is, the words seem scary, but they're not. All it is, that height is called the sine of the angle, sine of 40 degrees. End of story. So when you see the word sine, just think height of the sun. Ask, sine of 40 degrees, where's the sine of 40 degrees? And then I'll figure out how high it is. End of story. Now after a while, people became interested in other features of this picture. For example, you might be interested in how far over the sun is. What's the overness of the sun? And people started calling that companion length, the companion to the height, the cosine of 40 degrees, or what people abbreviate that as COS, cosine of 40 degrees, the overness of the sun. So all sine is height, all cosine is overness. By the way, you need to double check me on this part of the story, because I'm being a little bit loose here, because people realized actually what they're really thinking. They're still thinking sine, but they realized, if I do the picture here, that's 50 degrees, the complementary angle. That would be the height of 50 degrees, the companion angle, the complementary angle. So co actually means the sine of the complementary angle. But also it turns out to be the length of the companion side length. Whoa, whoa. So here's it. I think we've now finished our theory of circle-ometry, which means we've actually finished our theory of trigonometry, to be honest. There's only two things going on. If you want to work out this, there's only one thing going on, okay. Just figure out the height and the overness of the sun at a given angle of elevation for the simplest circle possible, radius 1, and we call the height sine and the overness cosine. And all you need is your common sense and your fabulous wits, and you can figure out the sine and cosine of all sorts of amazing angles, which I want to do next. But I'm going to need some board space. So here we are. We're now in the 21st century. We're going to be doing some problem solving, some thinking in our brains, just using our common sense to work out sines and cosines of different angles. The height of the sun, the overness of the sun at different angles, and it's just natural and easy peasy. So let's do it. Back in a moment. Okay, it's playtime. We just learned in the story of circle-ometry that the height of the sun is sine, the overness of the sun is cosine, at whatever angle of elevation you're talking about. So I don't know, your books might use X for angle, or A for angle, or Greek letter theta for angle. Doesn't matter, some symbol for angle. Great. Sine and cosine are just the height and the overness. Fabulous. Now let's work out some actual values of sine and cosine. And all you have to do is figure out where is the sun at the given angle. For example, if I asked for sine of 0 degrees and the cosine of 0 degrees, well, like I said, where is the sun at 0 degrees? That's all we have to figure out. So let me draw a picture. It'll make it look like a circle here, radius 1. Where is the sun at 0 degrees? It has 0 degrees of elevation. It hasn't risen yet. It's still sitting on the horizon in the east. So how high is that? No height. Oops, no height. And how far over is it? Well, remember it's a circle of radius 1, simplest radius possible. It's 1 unit over. Sine of 0 degrees is 0. Cosine of 0 degrees is 1. Done. What about sine of 90 degrees and cosine of 90 degrees? What you do is ask yourself, where's the sun at an angle of elevation 90 degrees? It's directly above me. Let's draw it. Okay, so here's the sun. Rise in the east, 90 degrees means it's up there. There's the sun. How high is it? 1 unit high. How far over is it? It's directly above me. It's neither left nor right of me. Got zero overness. Zero overness. Bingo. Sine is 1, cosine is 0 at 90 degrees. Beautiful. This is fun. What about sine of 180 degrees and cosine of 180 degrees? Let's do that one. Let me draw a picture for that. Get rid of this space. Picture's above this time. Where's the sun at 180 degrees? Let's find out. So, rise in the east, goes to 90 degrees over here, and it's setting in the west, right at 180 degrees. How high is it? Has 0 height above the ground. 0 height. And how far over is it? Well, this time it's over 1 unit, so I could say 1, that's fine. But let me make this a little more modern, because we actually are drawing axes here. We've got a positive x-axis and a negative x-axis, a positive y-axis and a negative y-axis. We're actually 1 unit in the negative direction. So just to give a nod to the fact that we've got a little more information here, let's say the overness is -1. It's -1 is 1 unit in the negative direction. That seems reasonable. I hope we can handle that. Great, and I bet you can see in your mind's eye, I'll pause for just a second, but what's sine of 270 degrees and cosine of 270 degrees? Where's the sun at an angle of elevation 270 degrees? It's directly below. So what's the height going to be? Can you see it's going to be 1 unit in the negative direction, and the overness is neither left nor right? Bingo. So once you have this picture in your brain, we're doing trigonometry. That's it. Well, circle-ometry, I should say. Fabulous. That's it. Now, of course, they're very, very nice angles. Let me do some more complicated angles. And this is where I love teaching this, because it's about teaching our wits, our common sense, the confidence to try to nut things out, which is fabulous, because that's what we need in the 21st century. Not the answers to these angles, but the process of thinking about how to get those answers. That's the innovation for 21st century world. All right, so let's try this one. Let's try this one. Sine is 60 degrees and cosine is 60 degrees. And that one is now going to be tricky. So we're going to rely on our confidence of wits. First of all, where is the sun at 60 degrees? Now remember, the sun always rises in the east, and 60 degrees will be about there, I guess. So 60 degrees will be something like that. There's the sun, and that's 60 degrees. Whoops. Terrible writing, but you notice that question. And I now want the height, sine, and the overness, cosine, for that triangle there for 60 degrees. Ooh, ooh, ooh. I don't have much to go on. I've got 60 degrees. I guess I have circle of radius 1. I've got that number as well. And that's it. That's it. I'm going to be scrambling. I guess that's 90 degrees. That's 30 degrees, but I'm not sure if that's helpful. Until I realize, oh, that picture is half of a very, very, very nice triangle. It's half a picture of a particularly nice triangle. Do you see what really nice triangles relate to this one? Well, if I flip this picture this way and just do the other one over here, do this length over here, I'll have 60 degrees there, I have 60 degrees there, and 30, 30, I have 60 degrees there. That's an equilateral triangle. So that's length 1, that's also length 1, and now logic tells me, oh, that part there, that overness is half of 1. It's a half. Cosine is a half. That's beautiful. Whoa, I'm halfway done. Now I need the height though. Ooh, the height. Okay, so let me just separate this a bit. What have I got? I've got this, this, and this. That's a half, the cosine. That's a 1, the radius of the circle, and I still want that height. And I guess that's still 90 degrees. My brain says Pythagorean Theorem. Let's just do a quick Pythagoras on this. Half squared, quarter, plus h squared should be 1 squared, 1. Quarter plus h squared is 1, so h squared must be 3/4. H must be root 3 over root 4, root 3 over 2. Bingo, we did it. Root 3 over 2. Oh, I love it. I love it. This is great. That's great. In fact, as you play with this one, I bet you'll find this sort of thinking will come up all the time. Look for a really nice half triangle, perhaps. Great. So let's do another one. Let's do another one. In fact, you might want to come back to this example in a moment, because I have a feeling it's going to be very, very similar. Let's work out sine of 150 degrees and cosine of 150 degrees. All right, we can do it. I know we can do it. Step 1, figure out where the sun is at an angle of elevation of 150 degrees. So let me draw a picture. Here's the circle of radius 1, and 150 degrees is 90, keep going, don't go all the way 180, we're going to go to 150 instead. So that's 150 degrees. And the sun is there. All right, now we want the height and the overness of that. Ooh, height and overness. Tricky. Well, when I look at that picture, it seems absolutely compelling to say that 150 is awkward. Let me think about the 30 that must be there. That must be 30 degrees in there. Now, that's much nicer. Now, is that picture half of a really nice triangle? And you might think, yes, it is. This time, flip it down this way. Draw the other part down here and here. That's length 1, that's also length 1. That's 30, that must be 60, 60, and 60 is an equilateral triangle, so all this is 1 again. And I feel like I'm in deja vu, what I just did before. That height now is a half. Can you see that? And now I've got a half squared plus something squared is 1. That's exactly the same work I was just doing moments ago right there. It must be root 3 over 2 for the overness, root 3 over 2. Except the overness is now in the negative direction, negative root 3 over 2. Beautiful. That's it. That's the name of the game. In fact, I bet you, as an exercise, could now work out sine and cosine of 330 degrees. I bet you could do that just fine. Draw a picture, figure out where the sun is. Don't work with the angle 330. Work with a different angle that seems nicer, and just use common sense thereafter. Grand. The power of common sense. This is what it's about, thinking. Love it. All right, let's now do a different type of triangle. Let's try this one. Sine and cosine of 45 degrees. Whoops, 45 degrees. Ooh, okay, we can do it. I know we can do it. So first of all, task number 1, where is the sun at an angle of elevation of 45 degrees? So rises to the east, and goes, I guess, halfway along to 45 degrees. Actually, that's interesting. I just said halfway along an angle. I'm wondering if that means it's halfway up in height. I mean, the whole height it could be is 1. Is that going to be 0.5, a half again? I don't know. Let's find out. Good question. All right, but we do know that's a radius of 1, and we want the height, the sine, and the overness, the cosine. And now I'm not sure what to do. Oh, bother. Okay, all right. Deep breath. What can I do? Well, 45 and 90, and I guess that's 45 degrees again. Great. Is that half of a really nice triangle? I feel like I'm going to be 45 and 45 again, or 45 and 45 again. I'll be sort of in the same problem. It's half a square. That's something. If I flip this way. Oh, but here's the thing. It's 45 and 45 and 90 is a nice sausage triangle. Whatever number this is, whatever the height is, and whatever the overness is, they're the same value. I wrote W for whatever. So, but now I can do Pythagorean Theorem. W squared plus W squared must be 1 squared, 1. So 2 W squareds is 1, so a single W squared must be a half. W must be square root of 1 over the square root of 2. Beautiful. Oh, that's it. The overness and the height are both 1 over root 2. 1 over root 2, 1 over root 2, and positive direction, positive height. Absolutely stunning. Fabulous. All right, your turn. Now put that on the board. Can you see in your mind's eye? Maybe you don't even need to draw a picture. Maybe you just do it in your brain, which is amazing. Sine and cosine of 315 degrees. Where is the sun at 315 degrees? Almost all the way around, except it's got 45 degrees to go to get back. So where's the sun in this picture? Can you see it's basically the same picture? I'm going to pause for just a moment. Okay, can you see it's essentially the same picture? The overness is going to be the same value W, but this time the height's going to be down there, negative W. Sine is negative 1 over root 2, and cosine is 1 over root 2. Wow. By the way, I will have a separate little video discussing that. I don't know what your curriculum says. Some curriculums say you can't have square roots on the bottom. Well, you can, it's actually fine, and might insist you rewrite it that way, which is fine. That's equivalent. I've got no problems with either way. All good, correct maths is actually good and correct, so both answers are good and correct as far as I'm concerned. But I will talk about that in another video to go with this. But here's the point. We can now work out the sines and cosines of all sorts of angles. Now, the standard curriculum, I think, wants people to focus on 0 degrees, 30 degrees, 60 degrees, 90 degrees, and 45 degrees, and these variations. That's fine. And you'll be coming up with these numbers over and over and over and over and over and over again. They'll start sticking in your head. Now, I think some curricula actually ask you to memorize them, so let me do something really sneaky, which I kind of disapprove of, because I don't actually think there's any need to memorize anything. But if you have a curriculum that does, I'm going to show you a very handy trick on how to get those numbers in your head if you're stuck having to do that. All right, so but to do that, I need to clean the board. Back in a moment. Okay, suppose you're in a situation you're meant to have the sine and cosine values of some standard angles in your head at an instant. I mean, I personally wouldn't memorize it because I can just quickly see pictures in my brain and just do it that way, or even just draw the picture, like, okay, spend 20 seconds drawing a picture. But anyhow, if you're in a situation where you need to have them in an instant, here's a very handy device. Turns out we usually are asked to memorize the sine and cosine values of 5 angles, 0 degrees, 30 degrees, 45, 60, and 90 degrees, which very handily matches 5 fingers on a hand. So here's my right hand matching each of the angles. Oh, actually, does this look like my right hand to you? What's going on? How am I doing this whole big screen thing and writing backwards? Oh, another mystery. Anyhow. Imagine your hand here represents with 5 fingers represents the 5 angles. Also imagine there's a horizontal bar across the bottom of the base of your hand with the number 2 below it. And also imagine there's a great big square root sign above your fingers. Now on the left is going to be sine, what I'm about to do, and on the right is going to be cosine. What do I mean by that? So, suppose I was asked to figure out the sine and cosine of 60 degrees. 0, 30, 45, 60. Put the 60 degree finger down. On the left is sine, on the right is cosine. Now I don't actually have it memorized, but I'm just quickly drawing the picture we did early on in my brain. I can see cosine's a half, and that must be root 3 over 2 for sine. Look, it's actually here. On the left, sine, root 3, 3 fingers, over 2. Root 3 over 2, sine. On the right, root 1 over 2, a half, cosine. Let's do 30 degrees. Put the 30 finger down, sine, root 1 over 2, a half, yes. Cosine, root 3 over 2, root 3 over 2, cosine, yes. 45 degrees, put it down. Root 2 over 2 for sine, root 2 over 2 for cosine. Crazy, it's correct. 0 degrees. On the left, 0 fingers, root 0 over 2, 0 for sine. Root 4 over 2, 2 over 2, 1 for cosine. At 0 degrees, correct. Ditto for 90 degrees. I can't even do that one. How do I do that one? All right, beautiful. There it is, a handy device if you need those values at an instant. But the thing is, actually, as you play with trigonometry, those values just stick in your brain. You'll start seeing root 3s over 2s, halves, and 1 over root 2s everywhere, and they'll just be in your brain after a while. Or, do this, or just draw pictures. It's all good.